With each captivating picture captured by the James Webb Space Telescope, it keeps on getting thought from various corners of the universe, including planets within our own planetary system. A year earlier, we pondered our first brief glance at pictures showing the Carina Cloud, Stephan's Quintet, and strikingly the hypnotizing deep field image. This particular picture apparently depicts different universes stretching out into the colossal expanse of the universe, fulfilling the assumption created. The James Webb Space Telescope hasn't stopped to surprise. It has recently uncovered objects that challenge established cosmological ideas. These astounding discoveries are now marked as universe breakers by cosmologists, confounding the scientific community with their ability to defy existing concepts. The reasons behind these revelations remain shrouded in mystery, throwing our theories and hypotheses into disarray. So, what's the latest scoop from the James Webb Telescope? What extraordinary new information has it uncovered that was previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence suggesting the presence of another universe, challenging the standard understanding of the Big Bang. Our universe, as we've long understood, arose from a hotter, denser state. Beyond a theory known as the Hot Big Bang, this idea, a significant scientific achievement over the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background (CMB), a remnant from the early hot and dense state. Over time, the Big Bang has remained the dominant theory explaining our universe's origins. However, new and critical observations have led cosmologists and astrophysicists to question both the continuous expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain momentum, emphasizing the enduring nature of the Big Bang theory. According to the general perspective, the description of the universe's origin involves a smaller, denser universe in the distant past. The presence of radiation, like photons, shows that the universe was hotter at its origin and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could form, and the normal laws of physics break down at around 10 to the power of -43 seconds during the Planck time. In such a brief period, small distances, brief durations, and high-energy scales challenge our understanding, rewinding the vast clock to the speculative zero point. If the universe began as hot and dense, then expanded and cooled, vast quantities of particles and antiparticles would have been created, with excess particles annihilated by radiation as temperatures dropped. The breakdown of the electroweak and Higgs symmetries led to the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions experienced growth due to radiation pressure, followed by gravitational collapse, leading to the development of large-scale structures about 380,000 years after the Big Bang. The universe cooled enough for stable neutral atoms to form, marking a critical step where photons decoupled, and their frequencies expanded as the universe grew. The discovery of the cosmic microwave background many years ago cemented the theory of the early cosmic explosion as the most supported explanation for the universe's creation. While most cosmologists and astrophysicists embraced the Big Bang theory, vigorous proponents of the steady-state theory, like Fred Hoyle, continued to defend increasingly unlikely cases, only to face defeat in the face of overwhelming evidence. The evidence presented was conclusive. It wasn't fading starlight or reflected heat from dust. The cosmic glow showed an astonishing consistency in all directions, resembling an ideal black body, yet it had no connection to known objects in the universe. Despite this, Hoyle and his followers continued to block scientific progress by supporting experimentally flawed ideas. Meanwhile, the fields of space science and cosmology experienced unprecedented growth from the 1960s through the 2000s, with cosmology seeing particularly striking advancements. We mapped out the vast universe and described its structure on a grand scale. We explored the development, evolution, and dynamic interaction of galaxies and their stellar populations. However, despite these advances, we encountered anomalies that defied explanation within the framework of the Big Bang theory. Observations revealed discrepancies that challenged the predictive power of the Big Bang theory, most notably the absence of exotic relics predicted by the theory, such as magnetic monopoles or particles from grand unification. The universe we see today seems to require forces beyond our current understanding, yet these remain elusive. At its inception, the universe required a precise expansion rate to balance the total energy density, an achievement that the Big Bang theory struggles to justify, attaining neither firm equilibrium nor sufficient time for energy exchange across various regions of space. Given the universe's vastness and its expansion over time, these anomalies present significant challenges for cosmology and the scientific community as a whole. When theories fail to account for observed anomalies, two approaches arise: refine existing theories or consider alternative explanations. The theory of inflation emerged as the most promising theoretical framework for expanding the Big Bang perspective. Inflation proposes a period of rapid expansion, smoothing out the universe and endowing it with uniform properties. It addresses the horizon problem and predicts the formation of quantum fluctuations, which manifest as density and temperature variations. Notably, inflation's predictions align with observed patterns and variations, supporting its validity. While alternative theories exist, inflation's scientific strength remains unmatched. However, despite previous contributions to general relativity and singularities, Roger Penrose's work, including his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the universe's earliest moments. Recently, there has been deliberate work to undermine the credibility of inflation theory, advocating instead for conformal cyclic cosmology, which is inherently flawed from a scientific standpoint. The key distinction lies in their predictions. Conformal cyclic cosmology posits that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory maintains that the point where inflation ends and a hot Big Bang begins should be causally disconnected from any pre-Big Bang region. Every aspect of our universe shows remarkable qualities, suggesting that we should rely on the universe itself to reveal what is true, rather than merely depending on speculation. Ignoring initial surprises, astronomers quickly recognized anomalies in the images sent by the James Webb Space Telescope. Since 2022, these revelations may require a reassessment of key aspects of the universe's origins and evolution. One major discovery made by the Webb telescope was the presence of fully formed galaxies much earlier than expected by the standard model of cosmology. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by the development of galaxies. Such discoveries disrupt our understanding, akin to encountering grandparents portrayed as children in a story. Moreover, recent evidence has uncovered anomalies within science's primary theories about the universe, such as the ongoing discrepancy in determining the Hubble constant, which persists despite improvements in data accuracy and collection techniques. Furthermore, new data from the Webb telescope intensifies existing challenges to the current cosmological model. These issues highlight flaws within the model itself, prompting questions among astronomers and physicists. While the model has undergone adjustments over the past 50 years to align with emerging data, some argue that these changes have been too convenient. As a result, there is growing recognition that a shift in perspective may be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe in the 1920s. Subsequent discoveries, like the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin, depicting the early universe as a hot, dense soup of subatomic particles gradually cooling over time. However, achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. Infinite expansion, proposed in 1981, was introduced to resolve anomalies in earlier Big Bang models, further highlighting the dynamic nature of cosmological theory. According to this theory, the early universe underwent rapid, extraordinary expansion for a brief period following the Big Bang. While some issues are resolved by this idea, new challenges emerge, particularly considering the common belief in the existence of one universe, potentially countless others beyond our observational reach. Certain observable anomalies, such as hypersingularities within black holes, find support through indirect evidence. However, the surprising revelations of the Webb Space Telescope regarding the formation of galaxies and the ongoing problem with the Hubble constant raises concerns that we may be approaching a tipping point where a significant overhaul of our current cosmological model becomes necessary. This could require a reassessment of the basic building blocks of the universe, including the very concept of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and the role of observers within it. The study of consciousness and quantum physics delves into similar subjects, exploring the intersection of theory and reality, challenging fundamental assumptions that support our understanding. Testing assumptions like the stability of physical laws over time has been proposed by scholars such as Roberto Mangabeira Unger and physicist Lee Smolin, who suggest that physical laws may evolve and change over time, challenging conventional wisdom. Physicist John Wheeler even proposes that each observation can influence the universe's past and future, profoundly reevaluating scientific practices. It is essential to examine these critical assumptions, given the impact of theoretical assumptions on data collection. History has shown that disruptions in scientific thought, such as the shift from geocentrism to heliocentrism, or the discoveries of evolution and relativity, have led to profound changes in cultural perspectives. A similar impact on our understanding might be expected from any upcoming scientific revolution in cosmology. Philosopher Robert Creighton argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. The ongoing debate centers around whether theory is needed to address cosmological fundamentals. If altering existing models proves insufficient, a complete update of our understanding of the universe may become essential. Recent advances in observational technology have revolutionized our understanding of the universe. The James Webb Space Telescope, with its cutting-edge instruments, allows astronomers to peer farther back in time than ever before, capturing light from the early universe that has traveled billions of years to reach us. This ability has transformed our perception of cosmic history, revealing patterns and anomalies that challenge long-held beliefs. One of the most significant implications of Webb's discoveries is the potential for re-examining the timeline of cosmic development. For instance, the discovery of mature galaxies just a few 100 million years after the Big Bang raises questions about the speed and nature of galaxy formation. This observation suggests that the processes governing star and galaxy development may have been more complex and efficient than previously understood. The implications of this challenge assumptions about the ongoing evolution of cosmic structures and propose that large-scale star formation may have occurred much earlier than current models predict. Moreover, the detection of extraordinary patterns in the cosmic microwave background radiation, combined with data from Webb, indicates that our universe may be more homogeneous and isotropic than the Big Bang model can fully explain. This has sparked discussions about the possibility of a multiverse, where our universe is merely one of many, each with its own unique properties. Such a paradigm would not only redefine how we understand physical laws but also extend the boundaries of scientific inquiry, as we may not be able to directly observe other universes. As astronomers continue to analyze the data from Webb, the potential for discovering exoplanets in habitable zones around distant stars has reignited interest in astrobiology. The study of the environments of these exoplanets could yield insights into the chemical signatures of life beyond Earth. Scientists are particularly keen to identify biomarkers, substances that could indicate the presence of biological processes. This search could ultimately lead to profound philosophical questions about our place in the universe and whether we are alone in the vastness of space. Additionally, recent discoveries from Webb have prompted a re-examination of dark matter and dark energy, two of the universe's most mysterious components. The anomalies observed in galaxy rotation curves and the distribution of cosmic structures may suggest new connections or particles that differ from existing theoretical models.